All right, so we're going to go backseat a little bit of linear algebra and now a little bit into multivariable calculus and see how they intertwine with each other. So that's pretty much what this sections are about. So vectors in a plane. So when it comes to these type of vectors, we're going to talk about three different types. So physical, geometric, and algebraic. So the physical is the ones that are actually physical itself, right? So like forces and velocity itself. Geometric is obviously just the actual geometric in the xy plane. And the algebraic is the ordered pair representation of the geometric vector. So basically this represents this, which represents that, like go up the ladder itself. Okay, so just a quick review of vectors in 2D. So a vector goes in roughly this direction, right, and from the origin up, and it also makes an angle, let's say like 65. Okay, so vectors have two things, a direction and a magnitude. Okay, so when it comes to a vector, usually it's denoted as a capital letter or in this format, where these lines represent the vector, not parentheses, not like a point. Okay, and we'll talk about how it's represented as a matrix in a little bit. But for now, we're going to break this down, right? So next thing is all geometric vectors have the same direction and magnitude will be represented as equal. That's a key thing, right? That going back to, again, multivariable calculus is if this vector is going in this direction, well, if this one's up here, as long as it's going, again, in the same direction and has the same magnitude, meaning the same length, they're considered equal vectors. So you can have an infinite number of vectors that are actually equal, again, as long as they're following the same path and they have the same magnitude or length, right? It's just a fancy word for saying the length of the vector. So how do we actually, formulate a vector? Given 2 points in the xy plane or in three-dimensional space, but for our case, it's always going to be just two-dimensional. So given initial point A and terminal point B, so it's going like from point A to point B. Vector V is represented as AB, again as the arrow pointing in that direction, and it's always end point minus starting point, which for each component. So for example, if B has B1, B2, and A is A1 and A2, so the vector V will have X component of B1 minus A1, and the Y component B2 minus A2. Okay. So again, a little review of just multivariable, basically, right? So let A, B, and B, C be geometric vectors. Then if they're equal, if and only if the components are equal, which makes sense, right? There's no brainer there, right? And we'll talk about, scalar multiples right now in a little bit, but for now, that's basically what our equality is going to be. So let's just do a simple example illustrating that fact. Okay, so let A, B, and C, D have those points, and we want to show that the vector AB is equal to the vector of CD. Okay, so first, we have to find vector AB. So that is, again, endpoint minus starting point. So you can see the endpoints here, starting points there. So -2 minus 4 gives you -6. And then the next one, 9 minus 6 gives you 3. And then CD. So this one again, 0 minus 6, so -6. And then 5 minus 2 gives you 3. And notice they're the same. Okay. All right, so now let's actually go into our portion. So physical is actually pretty difficult to do to show by, but we're just going to go up the ladder instead. So because again, one affects the other, right? So let's talk about algebraic vectors and how they look like. So algebraic vectors is just like the name, it's the algebra part of it, right? So again, this describes the geometric part, so one actually goes hand in hand with the other. So I have a starting and an end point, and it goes in this direction. So we'll call this vector V, where it's associated with points C and D. So vector CD, or just V itself, is in matrix format. So instead of doing it this way, which you saw in multivariable, now since we're linear, it can be represented as a matrix, and more importantly as a column matrix. Okay. So any vector in multivariable and going forward can be represented as a matrix in this format. So if you have 3, right, 1, 2, 3, in 3 dimensions itself. Okay. So quick little example. So let vector v be AB, where A is the points and B the points, and let vector u be this vector here. So A, represent V as an algebraic vector, basically make it look like that. Okay. So essentially, right, this is the same thing as just AB. So first times last, right? So -3 minus 2 is -5. 1 minus, 1 minus a -5, so that becomes positive. Yeah, so 1 minus 6, I believe. Yeah. So therefore, this is going to be like that. So that's our geometric approach. And now B, this is an interesting one. Represent U as a geometric vector with initial point C. So this is actually going backwards. So we're given the actual vector, and we want to figure out what was the points we started with, and we're given 1. And we're told this is our initial point. Now this is just going what we just did here, right? So vector U, and if I just go vector D is the point D1, D2, and let's say point C's, I know they have the points, but we'll just go in general so you can see what's happening. So if this is our initial point, so it can be this minus this, so it would be D1 minus C1 is the x component, and therefore D2 minus C2 will be the second component. Okay. So if I follow this process and now use the numbers we're given, where vector U is given to be 4, 7, is equal to D1 minus C1, which is 4 in this case, D2 minus C2, which is 9. Now we can solve for each individual component, right? So this just give me 4 is equal to D1 minus 4, and 7 is equal to D2 minus 9. So point D would just be added over, gives you 8, comma, again, add this over, gives you 16. So point D is the point 8, comma, 16. While C is the point 4, 9. Okay. Nice question. I always like to represent just the basic of vector additions and subtractions, right? So now let's go into actual adding vectors, right? How do we actually add vectors, not just individual points together? Okay. So let's suppose we have vector AB, or in shorthand, let's say vector U. And then we have from this endpoint to this point, vector V, which is the point B to C. So the addition of UV, or vector AB plus BC, would be this vector connecting like a triangle. Okay. And it doesn't have to matter, right? You could use arbitrary values. So let's say this was U here, and then go down here, this is V. So again, this sum here would be U plus V. So you basically just get a triangle when it comes to vector addition. Okay. So how do we do this? Well, how do we add vectors? Pretty straightforward. All we do is add component to component, right? It's pretty straightforward. Same thing with subtraction. We're just going to subtract component by component. Nothing too crazy there. And so we just have a theorem basically just illustrating that. Okay. All right, so now we go into scalar multiplication. Okay, so let's suppose we have a scalar multiplication, so starting at the center, and this is vector U. From the center to some point P. Okay, so again, U is some arbitrary point or arbitrary vector or matrix U1, U2. Okay. This is x, and this is y. Okay. So when it comes to scalar multiplication, all I'm doing is multiplying or dividing by a constant to this unit vector. So let's say s is some arbitrary number in the real numbers, right? So some number. And if I multiply s by u itself, all I'm doing is scaling the entire vector. So what that means is now instead of stopping here, just, let's say if it's doubled, now it's to double the length, right? So now this was originally p, so the entire thing now is su all the way to some point, let's say q here. Or I can scale it down, right? So if it was half, 1/2 times this, it would now be just half of it here, right? So I'm just stretching it, compressing it, depending on the constant of s in this case. Okay. Now, subtracting is component by component, but it actually gives you something very interesting when it comes to vector subtraction. So vector subtraction looks like this. So it's a subtle difference, but it does make a big difference in the long run. Now, when it comes to addition, the next vector will be added on from start to end, right? So it goes start to end, start to end. But this time, because we're subtracting, the starting points actually have the exact same point. So both vector u and v have a shared starting point, and the subtraction of these two vectors will give you the result here. Again, a subtle difference than addition. Okay. But again, you still get a triangle, a different triangle, because it gets more importantly as we go along in the next sections, but you still get a triangle. Okay. All right, so the last thing is parallel vectors. So parallel vectors are just literally just go in the same direction. That's all it really is. So because you can scale everything in 2 dimensions and 3 dimensions, anything that's parallel basically just means it goes in the exact same direction. It doesn't matter if it's scaled down or scaled up, as long as it goes in the same direction, they are parallel to each other. And that's pretty much it. So if vector u and v are parallel, if there is some constant c that when you multiply, it gives you the actual vector back. Again, all it is just a scalar multiplication. Okay. But here's a nice interesting part. We can have parallel vectors, and they can also go in the opposite direction now. Okay? But so we can say they're parallel but opposite direction. So obviously if the c is positive, that means they have the same direction. If c is negative, therefore they have opposite direction of it, which again makes sense, right? Just going in the opposite direction, but still technically parallel. Okay, and now we go into lengths. We talked about this a little earlier, right? The length of a vector. So given again any u vector, again we'll just use it as a 2-dimensional space for now. So the length of a vector, denoted as like a double absolute value if you want, is equal to each component squared added together. And then from that, we have something very special called the unit vector, where everything is scaled down to just one single unit. So every vector is scaled down, and it looks like this. We do 1 divided by the length of the vector times the original vector back. So let's do an example putting everything we just did together. So let V be the vector AB, let U be the vector CD, where points A, B, C, D are those. A, show U, V are parallel. Do the vectors go in the same or opposite direction? Okay, so, all right, so U goes from CD, so C to D. So endpoint minus initial, so -3 minus 1 is -4. Yeah. 1 minus 7 gives you -6. And now v, and phi is AB. So 3 minus 1 is 2, and 5 minus 2 is 3. Okay, so we want to show that these are actually parallel. So basically, if I can multiply by one of these by something that gets the other, so if it's easier, just go component to component. So, well, how do I go from 2 to negative 4? I got to multiply by negative 2 and see if it follows the same format. Well, if I multiply this by negative 2, yeah, I get negative 6. So if, according to our definition, right, vector u is equal to some c times vector v, and where that c is, that constant is negative 2. And so, since the c value is negative, they go in opposite directions. There we go. Now let's go on B. So find the vector k having the opposite direction of E, where the length of k is 10. So this is a bit of a trick question. So that's why I kind of like going over this kind of stuff. Something additional to just simply finding the length or the unit vector of stuff. Okay. All right. So first we got to find. Well, here's our v, right? We'll just start from there. 2, 3. Right, or v? Yeah, v. Okay. So first we're going to find the unit vector of v. Okay, so that's going to be, so 2 squared is 4, 3 squared is 9, so the square root of 13. Okay, so if we want the unit vector, so we call that w in the definition. So it's 1 over the square root of 13 times the original vector of 2, 3. Okay, so if I multiply this out, this is going to be 2 over radical 13 and 3 over radical 13. Okay. Now, we want opposite direction. So now I'm just going to tweak what we want based off this stuff. Okay, so opposite direction means I'm just going to change the sign now. Okay, so now we got to deal with this length of 10 stuff. Okay, so remember this is the unit vector, right? So this is just unit of 1, which is nice. So if I just want a length of 10, I'm going to just multiply this by 10 because, again, this is just 1. And 1 times 10 is 10. So you could rewrite it so it just be 10 times this vector. So again, you could do a couple of ways. You could just rewrite this out, just put 10 over 10 root 13 and just have the negatives there. Maybe that's like nicer to look at. Or you could just multiply it all in. Either way is the same answer. And so the last little major step is identity vectors, which is going to be really, well, I guess not very difficult, not difficult or algebraically, but another way to write matrices according to vectors. So we'll just do the 2 dimensionals, right? Because it's easier to do 2 dimensions, but this goes up to 3 dimensions with the jth component, the kth component. But for now, so the unit vector is basically where we have just 0, 1, 0 and 0, 1. So again, going from 0, 0. Okay. So this vector u is actually a combination or a linear combination of the identity vectors of I and j. So any vector u can be written using the ith and j component. In other words, this. So now think about this, right? This times this is just going to be u1, 0. This times this is just going to be 0, u1. And if I put these two vectors, I actually get the original vector back. So again, all this is another way to write vectors in different formats. Or you could see this as in multivariable, u1i plus u2j. And that's the connection to multivariable and linear algebra. We'll have more connection, but for now, that connection there.